Hey brothers, welcome. I'm your host, and as a wastewater engineer who spent plenty of time walking the tanks, I am so excited to dive into this explainer with you today. What we're unpacking here is basically your definitive field troubleshooting manual for one of the absolute most critical emergencies we can ever face out there: low-dissolved oxygen in our aeration tanks. We are going to break down the exact step-by-step protocols you need to diagnose and fix this issue right out in the field. Look, I want to hook you right away by reminding you of exactly what's at stake here. When your DO drops below 1 milligram per liter, or worse, below half a milligram per liter, we are officially in a code red level 3 emergency. This isn't just some minor hiccup or a weird blip on the SCADA screen. This is an active, immediate threat to the biological stability of our entire system. Literally every single minute counts. So here's our standard operating procedure for today. We'll cover the crisis, spotting the symptoms, finding the root cause, emergency fixes, the ultimate checklist, and finally prevention.
All right, part 1, the low DO crisis.
Brothers, you have to understand that a DOD drop cascades incredibly aggressively through our biology. It's like a horrible domino effect. First, cod oxidation just grinds to a total halt because our aerobic microbes are literally starving for air. Next, it suppresses those sensitive AOB and NOB nitrifying bacteria, which means you're going to see massive ammonia spikes at the effluent. Then, our beautiful, healthy flock structure completely collapses into dispersed growth, and it just washes right out of the clarifier. If we sit back and let this happen, we are looking at an agonizing 3 to 7 days just to recover our system stability.
Moving to part 2, spotting the symptoms.
Before the lab even calls you, you need to know what this looks like on the ground. If you walk the tank and see the water turning a murky, dark gray, or you catch that distinct, awful, rotten egg smell from hydrogen sulfide and we're captains, I need you to act immediately. You're also going to notice this thick, dark brown foam building up on the surface. And out in the secondary clarifier, you might actually see rising sludge because denitrification is happening exactly where it shouldn't be.
Now, the unseen chemistry driving those physical symptoms is wild. When your ORP, your oxidation reduction potential, crashes below positive 50 millivolts or even dips into negative numbers, it means your tank has totally lost its oxidizing power. Anaerobic and facultative bacteria just completely take over. They turn the sludge black and absolutely destroy our aerobic flock structure.
All right, part 3, finding the root cause.
To fix it, we have to hunt down the culprit, and I need you running these 6 diagnostic steps simultaneously. Delegate them to your shift operators if you have to. Grab a handheld and measure DO at multiple depths and zones, so see if the issue is just localized. Check the SCFM airflow and pipe pressure. Inspect the surface for dead zones, which usually means clogged diffusers. Evaluate your influent code for a shock load. Verify your DO sensors aren't just feeding you a bad 4 to 20 milliamp signal, and double-check if your MLSS is running too hot. This quick sweep tells us instantly if we're dealing with a blower failure, a clog, a toxic shocker, or just a bad sensor.
Okay, part 4, emergency fixes and scenarios. Once we know the cause, here's your timeline. Scenario 1, blower failure. If a blower goes down, your 0 to 2 hour emergency fix is to fire up that standby unit instantly. Manually adjust those valves to prioritize air to your absolute lowest DO zones. From 2 to 24 hours, get maintenance to inspect the check valves, air filters, and motor alignment. Long-term, say greater than 24 hours out, management really needs to step in and evaluate if your total blower capacity actually still meets the plant's design load.
Scenario 2, diffuser clogs. If your diffusers are choked up with scale or buried under grit, your first move in those opening 2 hours is to redirect air to the open zones or even isolate the working diffusers to increase the blowout pressure. Within 24 hours, you're going to be using high pressure or maybe acid and alkali chemicals to clear that scale. And long-term, guys, we've got to fix our preventative maintenance schedule so we are cleaning them regularly.
Now, dealing with a massive COD shock from production, that's a totally different beast. The equipment is perfectly fine, but the oxygen demand just went through the roof. You've got to max out the blowers right away and immediately divert incoming flow to the equalization tank, or at least dial back the feed valves. Within a day, pull some samples to find the source of the shock. Long-term, you've really got to push to upgrade your equalization capacity so this doesn't bite you again.
And hey, if your MLSS is creeping up way too high, say pushing over 4 or 5,000 milligrams per liter, that sludge is just hogging all the oxygen. Start wasting that sludge immediately through the WAS pumps to drop the demand and give the system some breathing room. Over the next 24 hours, gently dial your food to microorganism ratio back into that sweet spot, right around 0.15 to 0.3.
Moving on to part 5, the ultimate checklist. Brothers, I want you to mentally screenshot this list. When alarms are blaring, checking your DO at different depths, assessing surface bubbles for dead spots, verifying blower status and VFD signals, these are absolutely non-negotiable. And listen to me on this one. Do not blindly trust your automated DO sensors. Always calibrate them and double-check with a trusty handheld meter when things start going sideways.
Finally, Part 6, Prevention and System Stability.
Surviving the crisis is great, but true pros make sure it never happens again. We prevent this by keeping our standard operating DOs strictly between 2 and 4 milligrams per liter. You need at least 2 to 3 for active nitrification anyway. Get on a schedule to clean those diffusers every 3 to 6 months. Properly maintain your automated DO controls and have the lab run regular oxygen uptake rate tests. You want to anticipate what the system needs way before it turns into a 3 a.m. emergency.
Okay, here is the absolute most crucial takeaway I want to leave you with from the source material. It's the golden rule. Always design and operate with a 30 to 50% oxygen capacity buffer. You simply cannot run your blowers at 100% capacity every single day. Because guess what? When that unexpected COD shock hits, or when those hot summer temperatures lower the oxygen solubility in the water, you will have absolutely zero reserve left to save your biology.
Brothers, take this knowledge back to your plants. Sit down, review these troubleshooting protocols with your teams today, and ask yourselves a really hard question. If the SCADA alarm sounds tonight for critically low DO, is your crew actually ready to execute these exact steps and save the plant in under 2 hours? Something to think about. Thanks so much for joining me for this explainer, and stay safe out there on the plant floor.